Well, I will begin with a word of prayer as I get up here. Thank you. Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to study math together. I just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I want to talk to you guys today. My computer's doing something weird. There we go. About quadratic forms. So what is a quadratic form? So a quadratic form is basically an expression which only has quadratic terms. All right, so like I'll write out a couple of examples here. So example 1, we could have something like q of x comma y equal to x squared plus 4xy plus, I don't know, 2y squared, for example. That would be a quadratic form. Another example, we could have q of xyz equal to, let's say, x squared plus 3y squared plus 5z squared minus, let's say, 3 times xy minus 4 times xz minus 8 times yz. All right? So that's a quadratic form on R2, the first one. And the second one's a quadratic form on R3. All right? Notice that we've only got quadratic, like, terms. There's no linear term, there's no constant term. This is a quadratic form. Now, a quadratic form we can always write in terms of a symmetric matrix. All right? So like the first one, you can rewrite this formula as the row vector x comma y times a particular 2 by 2 matrix. All right? And this is what we would call the standard matrix of Q. Right? The standard matrix of a quadratic form. Which is different than the standard matrix of a linear transformation, right? Like a linear transformation is linear. Is a quadratic form linear? Like certainly not, right? If I put a constant into the form, if I multiply, well, we'll see it's nonlinear. Let me not do it in the current notation. We'll do it in a better notation in just a second. But first thing is first, let's try to figure out how to calculate the matrix of the quadratic form. And there's more than one answer you could put here, but we would like this to be a symmetric matrix, because if we make it a symmetric matrix, then we can use that real spectral theorem that we had last time to make the formula super nice. So let's use, we can always make this symmetric. So like I basically put a 1 here, and I put a 2 there because of that. All right? Now, in order to get this 4 here, I could, now don't write this down, all right? But I could put like a 4 here and a 0 here, that would work. But we don't like that because it's not a symmetric matrix. To make it symmetric, we take this 4, we put half of it here, and we put half of it there. Right? Now you can try, multiply that back out, you'll get back to where I started. All right? You can try it out, like multiply it out, see what happens. Now this one down here, I can rewrite this as a 3-row vector xyz times a 3 by 3 matrix. Right? I can write this as a matrix multiplication as well. All right? So let's see here. For the diagonal, I put a 1, a 3, and a 5. Because of the x squared, the 3y squared, and the 5z squared. All right? Now that minus 3 is annoying. That goes in the xy spot. So like, again, don't write this down. I could just put a minus 3 here and put a 0 here, but I don't want to do that. I want it to be symmetric. So what I have to do is do like minus 3/2 and minus 3/2 here like that. All right? That picks up this term right here. And how about that 4xz? Where's that? What's that do for us? There's a minus, right? So I would do minus what? Minus 2 up here, right? And also down here. That comes from that minus 4 there. And then finally, the minus 8yz. This piece right here puts a minus 4 here and a minus 4 there. So do you guys see how to do this? Like, this is the first thing. You need to be able to write down the matrix of the quadratic form. I think everybody can do this, right? Not a big deal. Once we have this, let me give you a more like general definition. So definition, we say Q, a mapping from Rn to R is a quadratic form on Rn if there exists a symmetric matrix A for which Q of x is equal to x transpose AX. And here I mean where, of course, I'm using x as a notation for the column vector, x1 through xn. That's a quadratic form. That's a convenient characterization of quadratic form for us, all right? Let's look at its properties. What happens when you do Q of like Cx? What happens when you put a scalar multiple into the argument? Let's study the properties of a quadratic form a little bit here before we do too many more examples. So if we have, we have Q of x is equal to x transpose AX. What happens when I look at Q of like C times x? What happens there? I get CX transpose, right? A, and then I got a CX over here, right? Which gives me what? I think that gives me C times C, which is C squared, x transpose AX, right? In other words, I get C squared times Q of x. Right? So is it linear? Well, I mean, I wrote the formula in terms of a matrix multiplication, right? But it's not a matrix column multiplication. It's a row matrix column multiplication. And clearly it's not linear, right? I pulled out C squared, not C. It gets worse. What happens if we try to do addition? Like, this isn't really even interesting, but what happens if you try to do like Q of x plus y? What would happen then? You'd have x, x transpose plus y transpose times A times x plus y. And if you multiplied this thing out, you'd get x transpose AX plus x transpose AY plus y transpose AX plus y transpose AY, which would give us like Q of x plus Q of y plus this thing. Right? I don't even know what that is. I mean, it's definitely keeping us from this being linear. I mean, additive. It's definitely not additive, right? Those are essentially like the cross terms when you square the thing out, right? Yeah. So, can we say anything then? Like, what can we say about the quadratic form? Well, definition, we can talk about the n sphere. This would be x in Rn plus 1 such that the norm of x is equal to 1. So like, for example, S1, what's S1? Explicitly, that would look like x1, x2, right, in R2, such that x1 squared plus x2 squared, square rooted, is equal to 1. Can you know what that is? What is that? That is the unit circle. Right, so S1 is the unit circle. S2 would be what? If I go to XYZ notation, we're talking about XYZ such that, yeah, x squared plus y squared plus z squared. I'm going to square the square root just to make it look prettier, but it's the sphere, it's the unit sphere, right? So it's this thing, right? It's not the ball. It's just like, like a basketball, just the surface of the ball. There's, it's not solid, right? The unit sphere. In physics, we sometimes call it like a spherical shell to distinguish between like a solid sphere. This is an ongoing unfortunate aspect of the English language, ball versus sphere, Anyway, great. So now we know what Sn is, yeah? So observe, if we look at q of x, we can write that as q of the length of x times x hat. Suppose x is not equal to 0, right? If x is not equal to 0, how do we define x hat? How do we normalize a vector, guys? Right, exactly. X hat is simply equal to x divided by the length of x, right? So if you rearrange that equation, you've got any vector, non-zero, is a product of its magnitude, length of x, times its direction, x hat. Every vector, non-zero vector, is a product of its magnitude and direction. So if we feed this to a quadratic form, well, use the property I just wrote there. My constant is the absolute value, the length of x, right? So I've got the length of x squared times q of x hat. So this gives me a theorem, right? Theorem, the values of q over Rn are governed by values of q restricted to the n-1 sphere. If I can figure out what the quadratic form does on the set of unit vectors, well, that completely reveals how it behaves elsewhere, all right? Now, why is that interesting from a math perspective? Well, we have a theorem called the extreme value theorem. And the extreme value theorem says that if your domain is compact, which is to say it's closed and bounded, then a continuous function will attain its extreme values. So like, theorem, since q continuous on the compact set S n-1, it follows that minimum and maximum values are attained for Q restricted to the n-1 sphere. How do you find those minimum and maximum values? Derivatives? Ah, yeah, that's not a bad answer. Unfortunately, we don't know calculus in here for some reason. But that would be a scary derivative because we're talking about, and it would be an n-dimensional function, right? So we'd have to do partial differentiation like the optimization problem. It's an n-variable optimization problem. That'd be kind of, that's challenging. But that's not a bad answer. Let's look at something. So I'm going to derive the minimum and the maximum values for Q on the unit sphere directly. Check this out. So if we have that A is symmetric, right? So we're given A transpose equals to A, and Q of X is X transpose AX, right? That's the formula for the quadratic form. Okay, then the real spectral theorem says what? Says there exists V1, V2, Vn, right? Think of them as a set, an orthonormal eigenbasis. An orthonormal eigenbasis, right? And I think I usually call that beta, right? So if you'll allow me this sideways E, there exists beta equal to that, right? And what we learned, like last class, is that if we multiply beta transpose times A times beta, it diagonalizes, right? We get a matrix of eigenvalues. Okay? You guys, we talked about this last class, right? Okay, so we still have that. It's a symmetric matrix. Let us define Y equal to the beta transpose times X, right? This would give us eigencoordinates. Eigencoordinate Y, right? Can you guys tell me how to rewrite the formula for Q? We have a Q of X is equal to, apparently, Q of what in terms of Y? If Y is equal to beta transpose X, can you guys solve for X? What's X equal to? Beta, I heard beta Y. Do you guys agree? What do you think? So we've got beta times Y. So you're saying that beta times beta transpose is the identity. Does everyone agree with him? I hope you do, because that's what we said last class. Beta transpose times the beta vector. It's an orthogonal matrix, right? The matrix with orthonormal columns is an orthogonal matrix. It transposes the inverse. So yes, that's my formula for X, so let's plug it in down here. So we got ourselves beta Y, yeah? And that is going to be, well, beta Y transpose that thing times A times, well, beta Y. But what are we looking at here? Well, we're looking at Y transpose beta transpose A beta times Y. Oh, hey, that's the diagonalization of A, right? So to write this out more explicitly, we're talking about y1, y2, yn times what matrix? What is this? That's the diagonal matrix with eigenvalues down the diagonal. So that's just lambda 1, lambda 2, lambda n, possibly repeated, okay? Times my y vector over here, which is y1, y2, yn. So guess what? There's a stone cold formula for the quadratic form in terms of the eigencoordinates. And the cool thing about this formula is we can write it down without explicit knowledge of beta. Beta's existence gives rise to the formula I'm writing down. We don't actually have to find beta to write this formula down if we know the eigenvalues. That's important because I ask test questions sometimes where I just say, write the formula for the quadratic form in terms of the eigencoordinates. You can do that directly once you know the eigenvalues. You don't actually have to find the eigenbasis unless I say work out the change of basis formulas. That's a different problem. So listen, it's just lambda 1, y1 squared, plus lambda 2, y2 squared, plus dot 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 dot, plus lambda n, yn squared. And there's the formula. Now this beta, right, is a orthonormal eigenbasis, right? So what that means, among other things, is that the coordinates, like what's the formula for the unit sphere in the eigencoordinates? I think I did some stuff earlier this semester where we looked at the distance between points in different coordinate systems, and we saw that if we didn't have orthonormality for the basis, like the distance formula was spoiled. However, if you do have an orthonormal basis, the distance formula is not spoiled. Like what I'm trying to say is the length of x is equal to the length of beta transpose times x. Because this, I can do a square here, do a square there. I don't have a square to spare. See here, beta transpose x transpose times beta transpose x, right? That's the dot product formula. Lo and behold, x transpose, beta transpose transpose, just as beta. We got a beta transpose, we got an x, and look at that. We got x dot x transpose x, which is otherwise known as x dot x. So there you go. This is the proof right here, should you choose to accept it, that the length of x and the length of y are the same, where y is related to x by a orthonormal change of basis. So what this all means is that we can write down the formula for the n-1 sphere in Rn. What's the formula? It's actually y1 through yn, right? Let me say it this way. It's x in Rn such that, y is equal to, this is just y is equal to beta transpose x, right? I mean, I'm just rehashing what we've done. And what's the formula? Well, the formula is just y1 squared plus y2 squared plus dot dot plus yn squared equal to what? Equal to 1, right? So the sum of the eigencoordinates squared equal to 1 is the formula for the unit sphere. So my question to you now, we've got a formula, right? Right here. Let me put a circle around it. If these coordinates, y1 through yn, if they're stuck on this sphere where the sum of the squares is equal to 1, what is the largest magnitude any one of those coordinates can have? 1. Or, well, the magnitude is 1. How about their values? They can range between what? -1 and 1, right? That's the extent that you're allowed. And you can't have it past that, right? If you had like 2, when you plug in suppose y sub 1 was 2. You plug it into this formula, you got 4 plus the sum of things which are not negative is equal to 1. Well, that's impossible, right? And in fact, if you make one of these coordinates 1, the rest of them have to be 0. So if you study this formula, right, what's the minimum and the maximum? Like, let's suppose, for the sake of specificity, that lambda 1 is less than or equal to lambda 2 is less than or equal to lambda 3, and so forth and so on, less than or equal to lambda n. In other words, I'm supposing that lambda 1 is the eigenvalue of the smallest eigenvalue. It could be negative. And lambda n is the largest eigenvalue. Could be positive. Could be negative, I don't know, whatever. But they're in order. What's the maximum, what's the minimum value attained on the unit, the n minus 1 sphere for the quadratic form? The biggest thing you can get is when you put in, you know, yn equal to 1 and the rest of them are 0. So like the maximum value would be lambda sub n, and the minimum value would be lambda sub 1. So in fact, the theorem then, you could write, that follows from this is like lambda 1 is less than or equal to q of x hat is less than or equal to lambda n. And that would tell us how to understand the values of a quadratic form on the n sphere. We simply need to find the eigenvalues, and those set the, that tells you the largest and the smallest it can be. Just like that. All right, let me I got some examples I should show you. I should actually show the pictures, because we need to look at some things. If I can get it. And once we look at these pictures, then I'll go back and I'll actually work one of these out in gory detail. Come on. If I can find my notes is the thing. Oh, I found it. Woohoo! All right. So I love this application. It is, oops. Hey, Corey, can you duck? Thanks. There we go. Bad line of sight from the camera on the pivotal formula. We got it though. We got it. Okay, so I love this application because, you know, this is one of those parts of linear algebra which I find myself needing in other classes, because oftentimes you find yourself with a quadratic form, that formula just appears in things, but it's hard to understand what it means geometrically without what we have in front of us. All right, so I want to kind of make that explicit for you guys. But before I do that, we need to kind of go back and just think a little bit more about curves and surfaces. Maybe you guys haven't thought about this recently, but we'll start out real basic. What's x squared plus y squared equal to 4? It's a circle of radius 2, right? Ah! No! Double, all right, there we go. So, on the other hand, you know, x squared plus 4y squared plus z squared equal to 1, this is a level surface actually in 3 dimensions. This is actually what's known as an ellipsoid. If we had, you know, if that was 1 instead, if you had x squared plus y squared plus z squared, well, that would give us the unit sphere. So this is kind of like a smushed sphere, right? All right, so I define the quadratic form in the matrix. Here, you know, here's the formulas. Yay, exciting. Some examples like we did. There's that proposition. I proved it. Come on. Here's some more. This is just like further elaboration of the proposition I was writing, which is basically just saying that if the value of the quadratic form was negative on the n minus 1. Oh, my index seemed, I had it upstairs. Now it's downstairs. Don't read anything into this. It's just, you know, I have trouble making choices. So, but it's traditionally upstairs, and the one that's downstairs is actually the symmetric group on n elements. But anyway, how many of you are taking Math 421? Doesn't matter. Okay, good. So what this means is just non-zero n space. All right. And what this theorem is saying is that if your quadratic form is negative on the sphere, it's negative everywhere. Except for the origin. It's always 0 at the origin, because if you plug 0 in, you get 0. Right? But if it's negative on the sphere, it's negative everywhere. If it's positive on the sphere, it's positive everywhere. And if it's sometimes positive, sometimes negative, then it's also likewise sometimes positive, sometimes negative everywhere as well. So here's a picture. So now what I'm doing is I'm actually graphing z equal to x squared plus y squared here. This is like z equals to x squared plus y squared. It gives us what's known as a paraboloid. All right. Now, if you look at like level curves of this, in the sense if you slice it at z equal to a constant, what do you get? X squared plus y squared equal to a constant is? Circle. So you get circular cross sections, right? If you cut it horizontally, right? You should always pray that God will section your enemies. It means cut them. Cut them.
They won't be perfect, sir.
They won't be well, okay. Now this one, x squared minus 2y squared. If we put z equals to this, we get this camel-looking thing, right? It's got humps. And so if you look at the sections of this, we end up with hyperbolas, all right? So like x squared minus 2y squared is a hyperbola, all right? Equal to a constant, it gives us a hyperbola. And if you set it equal to a negative constant, it gives you a hyperbola that opens the other way. It's hard to see that in this picture, but yep.
If you wouldn't mind going back up, it says consider the quadratic form.
Quadratic, yeah, it's quadratic. So that'll happen. Oh, look harder, you'll find more. So, see, if you're amused by this just means you haven't read my notes. Because you would know.
I've read them.
Okay, good. But so here, this is another quadratic form, which is kind of boring in the sense it's just 3x squared, right? And so if we set that equal to a constant, we just get x is equal to like, plus or minus that constant divided by the square root of 3 or whatever. But if we graph z equals to 3x squared, it gives us a parabolic trough, right? That's what that would look like, all right? Now, so all of these formulas are very simple. There's no cross terms. It's just pure squares. Like here is x squared plus 2y squared plus 3z squared. To visualize that, you could look at level surfaces. In other words, what we're looking at here is like x squared plus 2y squared plus 3z squared equal to constant, a different constant, a different constant, a different constant. So it's like an onion, just kind of fills all of space with the different level surfaces of that quadratic form in 3 variables. All right. So this is the theorem I just presented for you guys on the sideboard over there. Come on. So here's one that's interesting. Suppose we've got q of xy equal to 2x squared plus 2y plus 2xy plus 2y squared. Now, when you just look at this, and then I say, if you set that equal to a constant, what do you have? Is it an ellipse? Is it a hyperbola? Is it a pair of lines, like x equal to plus or minus something? Like, what is it? You can't tell, right? Because it's got that pesky cross term, right? Nobody asks you to graph this in your pre-calculus class, right? You don't have formulas for this. But we can find the formulas because all we have to do is write it as a quadratic form, like so. Find the eigenvalues, which are 1 and 3, all right? Then that gives us this eigenvector and that eigenvector explicitly. Here's your orthonormal eigenbasis. Notice I divide by square root of 2 now because I want it to be normalized to length 1. That's what's going on here. We didn't care about that earlier when we were just solving differential equations. We didn't need length 1 vectors, so we didn't bother, But now we will bother. So we can find, I'm using bars here. All right, so like in the abstract discussion over there, I used x for the initial coordinate and y for the transformed coordinate. Obviously, if I'm using x and y as scalar variables, I can't use that notation, right? So my usual notation is to use the original Cartesian variables like x, y, and then to use the rotated variables x bar, y bar. That's my notation here. So my y vector x bar, y bar, so to speak, p transpose x. Now, this is my p, and so I get these formulas. X is equal to 1/2 of x plus x bar, y is equal to 1/2 of minus x bar plus y. Or you can solve these for x bar and y bar as such, all right? So then what I'm going to do is I'm going to take these formulas, if you like, and I'm going to plug them back into the the original formula for q and see what happens. Yeah? And if we do that, what happens when we plug in x equals to this and y equals to that into the original formula x squared plus 2xy plus 2y squared, this happens. The formula simplifies in the eigencoordinates to just this and that. And this is in complete agreement with what I wrote in the board over there. Lambda 1 is 1. See the 1 here? Lambda 2 is 3. See the 3 there? Well, 3 you can see. And then we can visualize what's going on here. You see, I said x squared. I meant 2x squared. So if we, again, if we plug these formulas in, like just substitute these formulas into this expression down here, this thing ends up canceling out with the other pieces because of the minus here and the way it all comes together. So in short, when we look at this equal to a constant, we can see that what we're looking at, the answer to my question, what is x squared, 2x squared plus 2xy plus 2y squared equal to, say, 1? What is that? It's an ellipse, is what it is. That becomes manifest if I put this right here. Come on. If I put this equal to 1, of course it's an ellipse, because it's the sum of the squares of two variables equal to a positive constant. Like that's an ellipse, right? Now here's a picture, which is a bit busy, but that's a picture of the this thing right here. These are the planes in which the eigenvectors point. So it's like the eigenplanes. That's like x bar equal to 0 and y bar equal to 0. So those are the eigencoordinate planes. And with respect to the eigencoordinate planes, this this thing is well, anyway. I wish I had a different picture here. Oh well. Let me try to add a picture if I can. I was stuck on 3 dimensions when I made these notes. Let me be a little bit more 2-dimensional on that example. Let's add a picture here. All right, so let's go back up. What was the eigen? U1 was 1 minus 1. So here's x and y, right? U1 is 1 minus 1. That's 1 over, 1 down. So that's like this. All right, so that's the x bar coordinate system. And the other one, U2, was 1, 1, right? So that's like this up here. So the x bar and the y bar coordinate axes are like that. So as we think about the formula for this ellipse, right? And we said it was what? If we look at, for an example, I was posing the question, what is 2x squared plus 2xy plus 2y squared equals to 1, right? So if you believe me, if we plug in those coordinates, this translates into x bar squared plus 3y bar squared equals to 1, right? So, here's my eigencoordinates. So you guys tell me how to plot this. How do you figure out the formula for the ellipse? What do we do? Like what I do is I put y bar equal to 0. That gives me x bar is plus or minus 1, right? X bar is plus or minus 1, let's say. All right. And the x bar. Now if I put x equal to 0, I get 3y bar squared equals to 1. So y bar squared is 1/3. I get plus or minus 1 over root 3. What's 1 over root 3? Smaller than 1, right? So, I don't know, it's like maybe here and here, right? It's like 1 over root 3 minus 1 over root 3. And so what I have then is an ellipse. But what kind of an ellipse do we have? Yeah, it's a rotated ellipse. It's been rotated, in fact, by 45 degrees. And we can discover all this by writing down the quadratic forms matrix and diagonalizing it, finding the eigencoordinates that will reveal the hidden formula. Like that, yeah? Does that make sense? Do you guys understand the method? I always tell calculus, like I would explain to you the cross terms, but I can't because we don't have this class, yeah? Now, this picture is harder to, like this picture is harder to understand. Like, I mean, if you don't understand the picture, it doesn't matter, frankly. I probably should redo these notes and get rid of these horrible pictures. The website which I made these pictures with it died in the Java apocalypse of 2010 or whatever. I don't even remember. It's been a while. These websites, they come and go. These poor academics, we labor to make things of lasting value, and then the computer science people and their fickle security blah, 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 make everything fall apart. It's so annoying.
You could remake it in GeoGebra.
Remake it in GeoGebra. GeoGebra is fine for now, but there will come a time when GeoGebra is not safe. It's just a matter of time. I wish I was wrong. Let me be wrong. I guess MATLAB will probably live on. All right, so we just talked, so here's the next one. X squared plus 2y squared plus y squared, right? What's the deal with this? Like, if you put that equal to 1, what are you looking at? I don't know, right offhand. But if you look at the matrix of the form here, it's just 1, 1, 1, 1, which you can immediately see has an eigenvalue of 0. Why do I know that? How do I know the matrix 1, 1, 1, 1, 1, 1, 1, 1 has an eigenvalue 0? Well, it's the same column vector repeated, right? It's linearly dependent, therefore it's a singular matrix. It's not an invertible matrix. If it's not invertible, it must have eigenvalue 0, right? Anyway, as you can see, that happened. So there's eigenvalue 0, eigenvalue 2, and here's your eigenbasis. It seems like it always works out to this for us at the moment. And what that then means, and you can probably look, like this one's kind of obvious. Like, can you guys see how to simplify the quadratic form from the start? Like, you'd probably still have a chance at this one, even if I didn't tell you anything else this semester. Like, what is this? It's x plus y what? No? Yes, x plus y squared. It's just literally x plus y squared. So it's not too surprising in view of that the eigenformula for it is just 2y bar squared. And notice that y bar is, y bar is x plus y. So you can almost see it like directly, right? Like the formula is x plus y squared, right? And so, of course, x plus y squared is 2y bar squared, right? Put the 2y bar, you have 2y bar is equal to x plus y. So x plus y squared is, 2y bar squared. I feel like I might be missing something. It feels right. It feels off a bit. I'm missing something. Maybe that, I feel like that should be a, what? All right, I'm gonna stop. My brain's not braining. All right, well, you guys are not inside my brain, so let's go on. Again, here's a picture. It's easier to see that it's a rotated parabolic trough, right? You can, that I can see. Next one here, 4xy. What is 4xy? If we set 4xy equal to 1, what is that? This one you could actually graph, right? Think about this. If you're asking what's 4xy equals to 1 for the sake of discussion, this would be what? Y equals to what?
1 over 4x.
Yeah, 1 over 4x. That we can graph straight up. It's just this deal, right? Right? But what is that? Well, let's find out. So we write down the quadratic form, which is what? Dudes. That's a typo. Good grief. How did I not see that? Sadness. It's fixed down here though, right? 2, 2. That's what we should have, right? And so we got eigenvalues -2 and 2. And as such, here's my eigenvectors. And lo and behold, the formula for, and I put a tilde here because technically speaking, it's not the same function. So I'm just, being mathy. Anyway, the formula in terms of the eigencoordinates is -2x bar squared plus 2y bar squared, which shows you that, in fact, this is a what? It's a hyperbola. So it's a hyperbola where the coordinate axes are the asymptotes. All right? And the, yeah. So it's a hyperbola rotated 45 degrees, and there's the graph z equals to that as well. All right. So here's one that's a three-dimensional example. I just started us out with the matrix, right? Here's the matrix of the form. What are the eigenvalues of it? Well, if you calculate the characteristic equation, the eigenvalues of this contraption are 4, 8, and 5. Yeah, 4, 8, and 5. What's that? If we put w equals to this, it would be 4-dimensional. So all we could hope to do is put that equal to a constant. Then it's a surface, right? This is always the struggle. It's like, how do we want to think about a function of 2 variables? If we put z equals to that, then we have to think about a graph in 3 dimensions, right? But if we take a function of 2 variables, we set it equal to a constant, that gives us a level curve, right? And if we let that constant change, we can think about a family of level curves, which is a 2-dimensional way of understanding a 3-dimensional shape in terms of its slices. This is the idea of a contour plot.
So technically the last problem you would classify as 2-dimensional, like the one we did before.
Yeah, those are 2-dimensional problems. It's just, I'm going to the trouble of graphing it in 3 dimensions just because that's another thing we can look at, and I was just trying to show off, really. So I said, shut up. Anyway, so these are the eigenvectors for those eigenvalues, respectively, 4, 8, and 5. This, that, and that. All right. This one's unsurprising if you go back and look at the matrix. And as such, we get these new eigencoordinates, such and such. Well, z bar is equal to z, so that's z. There's nothing happening with z. And when you switch over to these coordinates, we get 4x bar squared plus 8y bar squared plus 5z bar squared. And so we can see that if we set that equal to a constant, we're looking at an ellipsoid. Yeah.
You're looking at an ellipsoid and it's rotating. It's just rotated around.
It's rotated like this. So I think z is this way, or oh man, I need the axes labeled in this thing to make sense of the picture, but it's a tilted ellipsoid. So like one of the axes is like this, right? Another one's like that. And then the one that's unaltered, I think, is just straight. I think this is z, actually, in this picture. Okay, so this is the theory of quadratic forms. We can write down the matrix and diagonalize it to discover eigencoordinates to make the formula simple. Now, in view of all this, what is the eigenformula for this one? Blank times x bar squared plus blank times y bar squared plus blank times z bar squared. What will we fill in the blanks here? If we wanted to write example 2 in terms of eigencoordinates, what would we do? Well, if we wanted to suffer greatly, Wait, is that your problem? Might be your problem. Wait, where did I? Anyway, let me just show you. I should not show you my trade secrets here. Let's see here. ChatGPT has opened up a whole new vista of stupid problem making for me. Let's see here. Let us do the thing. All right, so I like the old version of this calculator personally. All right, so you guys help me out because I can't see behind my head. What is the matrix for example 2? Was what, 1? Okay. Okay. Mm-hmm. 3. Okay. What's the last? 5. All right, so we calculate the eigenvalues and the eigenvectors. As you can see, all real eigenvalues, no surprise there, right? And up to the limits of my... All right, let me try. So minus 2.05. And then my next eigenvalue was 2.89-ish. And my third and final eigenvalue was 8.19. So there you go. That is an approximation for the formula in example 2 using, I'll get this stuff out of the way here. The diagonalization, if you will, of that matrix for all right, so let's see here. Let's look. So did you get the method? I mean, it's, so now if we, I don't really have language. It doesn't really matter. If you were in Calculus 3, you might have a name for this. Like what happens if we put this equal to a constant? No, there's a minus here. That's a question. Is it 2 sheets or is it 1 sheet?
1 sheet because there's only 1.
1 sheet, there's 1 minus. That's right. So if I put this, basically, if you think about putting this equal to a constant, you could rewrite this as 2.89 y bar squared plus 8.19 z bar squared equals to that constant plus 2.05 x bar squared, right? And so if you set x bar equal to, x bar naught, then what do you have here? It's a circle. Radius r is the square root. Well, it's not a circle. I'm an idiot. Is that a circle? No. Ellipse. Right? It's an ellipse. Because this, okay, fine. Oh, wait a minute. Oh, that depends on the value of the constant, doesn't it?
The hyperbola.
Yeah. Because if the constant is positive, then this is minus plus plus. But if the constant is negative, you could view this as plus minus minus. It matters. So we're both right. It's a hyperbolate of 1 sheet or it's a hyperbolate of 2 sheets, depending on the value of the constant. If the constant's equal to 0, what is it? What's between hyperbolates of... Really? California. I don't name it California. Go away. It's just Xfinity trying to sell me. But I'll never buy. So, all right, so, get away. If we had the constant was equal to 0, we get a cone. So like you have a cone, then you have in between the, oh here, did you guys know about this? How many of you had Calc 3?
Are you talking about conic section?
Yeah,
I forgot about that.
come on. Here, let me show you something real quick. So if we look at my multivariate calculus website just for a second here, just so you know what I'm talking about. If we go to the zoo, I have pictures. In fact, this is the picture right here. What you're looking at there is the wireframe is the cone. All right, and then the thing which is graphed actually is either the hyperboloid of 2 sheets or 1 sheet, you see. Depending on whether the constant is equal to a positive or a negative. And like the formula for this thing that we're looking at the moment is up here. It's, I think, I've written it as xx plus yy minus zz, so it's x squared plus y squared minus z squared equal to a constant. And that will either give you, for the constant 0, it gives you the cone. And you know, whether the constant, when the constant's negative, it gives us 2 sheets. When it's positive, it gives us 1 sheet. So, yeah, you're right. 1 minus for 1 sheet, 2 minuses for 2 sheets. Yep. Very good.
Say 1 or 2 sheets?
Well, there's 2 sheets, 1 sheet.
That's 1 sheet.
1 sheet.
Yeah, that's what I thought.
1 sheet, 1 sheet, 1 sheet, 1 sheet, 2 sheets. All right, there you go. So, exciting, yes? Okay.
It's like watching the TV signal like bouncing.
Oh, yeah. All right, so listen, this brings us to, I was trying to talk a little bit here about optimization. I'm trying to find the right formula for us to look at. So here is the formula for a function of 2 variables. If I have f of a plus h1, b plus h2, I can write that as f of ab plus h1 times the partial derivative of f with respect to ab at ab, partial derivative of y at ab, and then plus 1/2 this thing. All right? Now here's the thing. If you're at a critical point, right, when we study in calculus, the maximums and the minimums happen where the derivatives are all 0, right? So at a critical point, the x and the y derivatives are both 0, which means that the function, we have f of ab plus this piece over here, you see? So basically, the values of the function close to a critical point are dominated by this. What is this? Well, this is a quadratic form in h1 and h2, which are simply the change in x and the change in y really close to the point, the critical point. Let me write this down over here. Now, I don't expect you guys to, I will, well, anyway, I need to remind myself what I gave you in the homework before I say much more. But, so, essentially, here's the deal. We have f of a comma b is equal to, if we look at it, h1, h2, times this matrix, fxx, fxy, fxy, fyy, times h1, h2, right? And I guess there's a half. There's a half here too. Is there a half? Yeah, there's a half. So I put the half out there. And so here we have f of a plus h1 comma b plus h2, all right? Given that the gradient of f at the point AB, which by the way is fx at AB, fy at AB, if that's equal to 0, 0. So if we're at a critical point, then the formula for the function in terms of the multivariate power series, and yes, there is a multivariate power series. Now, if you didn't take Calculus 3 with me, you don't know about that because it has been carefully hidden in Stewart's calculus book, and if you teach from the book, then you'll remain ignorant.